Welcome everyone to today's lecture on the topic of forces involved in circular motion. So we have already studied what are the other elements of the motion when a particle is going in a circle. For example, what is the velocity of a particle? How do we write the velocity vector of the particle when it is going in circular motion? What is the acceleration of a particle when it is going in circular motion? And what is the expression of centripetal acceleration, what is the expression of tangential acceleration, and how they manifest in some real life situations. So the question then comes out about that what is the forces which are responsible for producing the accelerations which keep particle going in a circle or in curvilinear motion. So one of these forces is centripetal force. So there are plenty of real life examples from which we can take up and think about that how centripetal forces operate in nature around us. For example, let us take the case of a particle being whirled in a circle when it is attached to a string. So let us attach a particle to a bob. So this particle, we have named the particle as some bob, and this bob is connected to a string. So this is a common situation where we connect a string to a bob or a ball and we whirl it in a circle. So in this case we are not considering any gravitational forces acting on a particle, the gravity is absent and it is being whirled in a circle like this. So the idea is that what are the forces acting on the bob? So we already know it is connected to a string, so there should be some tension force acting on the bob. So this tension force is some T, let's say, we have labeled it as T, and it is being whirled in a circle with uniform speed. So what law are we going to apply in this particular situation to study centripetal forces? What is a centripetal force? So is centripetal force a force which acts on a particle when it is going in a circle, or it is the name given to the forces acting on a particle which are keeping it in a circular motion? So let us see. So Newton's second law says that the net force acting on a particle should be equal to ma. So the force acting on a particle when it is going in uniform circular motion, it is going with a constant speed. So this force should be this tension force, and this acceleration should be equal to the acceleration of the bob. So the acceleration of the bob we can find by evaluating what is the velocity of the bob and what is the radius of the circle in which the bob is going. Because the bob is going in a circle of some radius r, which we have taken arbitrarily. And what is the acceleration of the bob? The acceleration of the bob is centripetal acceleration. And what is the expression for centripetal acceleration, which is a? So the expression for centripetal acceleration is v square upon r. So v square by r is the centripetal acceleration. So we multiply v square by r with mass m, and we get the sum of all the forces acting on the particle when it is going in uniform circular motion. So this is the expression for centripetal force, mv square by r. This is the expression for centripetal force. And what is the force acting on the particle in this case? The force acting on the particle in this case is tension. So we say that tension acting on the bob is equal to mv square by r. So what is centripetal force? Centripetal force is the net force which acts on the particle when it is going in a circular motion, and that force is directed towards the center of the circle. Since we have already evaluating the forces which are directed towards the center of the circle, so that force is called the centripetal force. So in our case, the centripetal force expression is mv square by r. It is not in our case, in all the cases the expression is going to be mv square by r. In our case, the centripetal force is the tension. So let us move on to some further examples to further study how this force acts in the world around us. So the first example which we are going to take, which is going to demonstrate the idea of centripetal force, is the motion of a car on horizontal road. So this is a common scenario which we know. A car is going on a flat banked road or non-banked road. What we mean by banking? By banking we mean a road which is inclined at some angle and it's a curved path. So the topic which we are saying is motion of a car on horizontal road. So when we talk about horizontal roads, we are imagining a situation like this, that you have some curve on which the car is going. Let's say the curve has some radius. So the radius of the curve is some r, and the car is going like this. So it is going to complete its whole complete circle, and is going with some uniform speed for the simplicity of this case, for our sake. So this is the speed of the car, which is v. Car would be having some mass again. So the point is, what are the forces acting on the car, which we will quantify as centripetal force or classify as centripetal force. So what are the forces acting on the car? So you can say, sir, there are 2 tires for this car which are visible. There are 4 tires for the car, and all the 4 tires there will be some normal reaction acting on the car. So what would be the normal reaction acting on the car? It is the normal reaction would be acting in this direction, upward direction. It would be having some value. It would be equal to the weight of the car. So there would be some normal force, which would be combination of the forces acting on the tires, and it would be gravitational force mg. We are taking the car which is traveling on earth, and there would be some frictional force acting on the car. So what frictional force would be acting on the car, and in which direction would be acting? So the point which we are going to discuss is first, that is the car accelerating or not? Car may be accelerating, and if the car is accelerating, let's say it's going in a straight line, then definitely there should be some forces which would be pushing the car in forward direction, right? It is not a jet car. So that's why it is being pushed ahead by the motion of its tires, the mechanical motion of its tires. So the car, when it would be going in a straight line, it is being pushed ahead, or it is being accelerated ahead by the forces of friction, right? And if the tires of the car are not slipping, in that case we say the forces acting on the tires of the car is static friction force. So that is the main point which we are going to consider. Even here, even in this case, when the car is not going in a straight line, right? The car is not going in a straight line, it is going in a curved path. So how does it relate to the case which we have taken? The car is going in a straight line, it is accelerating. In both the cases, the tires of the car are not slipping on the road. So the tires of the car are not slipping on the road, which means that there is no slippage between the particles of the tires and the road, which means we are going to take the case of static friction, even if the car as a whole is moving on the road. For example, if we were to replace this car with a block, right? Let's say there is a block and it's going with some speed v. So would we say that there would be some kinetic friction acting on the block? Yes, we would say that there should be some kinetic friction acting on the block, because between the tires or between the particles of the block and the road there would be some sliding, right? And we won't be able to take the case of static friction. So what would be the friction acting on the car? We know the answer for static friction, because there is no slippage, and this can be visualized, right? We are able to visualize it. So the friction force is acting. The next question is, in which direction the friction is acting? So that is even answered by what we considered earlier. We considered earlier that the car is moving in a straight line. It is moving in forward direction with some increasing velocity, with some acceleration. So it has been pushed ahead with some frictional force, and there is no slippage. So in which direction was the acceleration of the car was there? The acceleration of the car was in forward direction, right? So because the acceleration of the car was in forward direction, it required a force in forward direction. And in the same case here. Now it may not be easy to visualize like we were able to visualize in that case, but in this case too, the friction force acting on the car has to be in the direction where the friction where the acceleration is required. The acceleration is not required in forward direction. That is along the line in which the car is going. There is a line along which the car is moving, that is a circular line. That is not important. The important part is in which direction the acceleration is there. The acceleration is perpendicular to the line in which the car is moving. So the friction force will act in the direction in which the car is, in which the acceleration is there. And there is no slippage. The car is not slipping outside or not slipping inside. If it were to slip, then there should have been some static friction, and because it is not slipping, the forces acting on the car is a static friction force, which we now are labeling as F only. But if we were to think, then it would have been static friction. So let's say some friction force is acting on the car. So again, just like in the case of the string which was attached to the bob, there was a force acting on the bob which was acting towards the center, and it was equal to mv square by r. We can easily say that the friction force is the only force acting on the particle which is keeping the car in circular motion, and its value should be equal to mv square by r, which is the expression for centripetal force. So this is the expression which we are going to obtain, which we were trying to obtain, that what is the friction acting on the car and what is the relation of friction with velocity and the radius of the circle in which the car is moving. Now we know we can find the value of friction for a particular speed of the car. So if we are given the speed of the car as some 10 meter per second, what should be the friction acting, and so on. And definitely if the speed increases, and even at 10 meter per second, the car may slip. So what are the conditions of slipping of the car? So let us take the limiting case. The limiting case, we say that the value of friction when it reaches to its limit, that's why we say that it's a limiting case. In that case, the value of friction is mu ng, right? So when we are maximizing the value of friction, taking the maximum value of friction, what we are trying to do? We are trying to take the car with the maximum possible speed on this bank curve. The car would be able to speed with the value of, with a small speed, it would be able to move with a no harm, right? It would require some small values of friction, but it would be able to move without increasing the value of friction required. But when we are trying to increase the value of the velocity of the car, increasing the speed of the car, then the friction on the car should be more. Its value should be, its value required is more. That is the point, which we can see easily. For example, if we are going with the speed v, so the value of friction required is f. if we are going to increase the value of speed of the car, let's say v goes from v to some 1.5 v, then friction would definitely increase. 1.5 square would be more than the value of v square. So friction increases, and can we provide that friction? So that comes out to be the answer which we are looking for, that this is the value we can provide, mu mg. If the value of friction provided is less than mu mg, very good, the car would be able to move in this horizontal circle with much ado. But what happens if the value exceeds? The car would slip, and this friction would turn from static to kinetic. So the value of mu mg matches mv square by r in the limiting case. So this is the maximum value of the car's speed with which it can move in a horizontal circle. So this is the max speed, the maximum speed of the car with which it can move in horizontal circle. So its value comes out to be mu gr, or V max is equal to square root mu gr. So this is the value of the maximum speed which we can obtain, and for a car moving in a horizontal circle. So what was the centripetal force in this case? Not the normal force, not the gravitational force, the frictional force. And since we are talking, there is a gravitational force over there, can we think of an example in which gravitational forces are involved and gravitational force acts as a centripetal force? Particularly when we talked about a definition that the force is acting on the particle towards some center of the circle, which keeps the particle moving in the circle or in a curve. So what we are talking about is, can gravitational force act as a centripetal force? So you would have guessed it right. That is, when gravitational force acts on any planet going in a solar system or any star going around the center of Milky Way, which is our galaxy, or any on the moon when it is going around Earth. So all these forces, the gravitational force, are keeping those planets, those heavenly bodies in motion around the bodies which are exerting the forces on them. So all these forces are acting towards the center, and these forces are keeping those bodies moving in some curvilinear path around those bodies. So these are the centripetal forces. Now let us do a question. So we have a car. So the car is moving on a circle of radius some 30 meters. Radius of the circle is some 30 meters, and the car is moving with the speed of some 10 meters per second. And let us say the accelerated gravity is some 9.8 meter per second square. So these are all data given to us. The car is moving with the speed of some 18 kilometers per hour. So 18 kilometers per hour would be some 10 meters per second only. Let us take the data. So 18 kilometers per hour. So the car is moving on the horizontal surface. That is the case is same as what we have taken. So the idea is we have to find the value of coefficient of friction of the car, of the road. We have to find the values of coefficient of friction of the road and the car's tire, so that the car slips on the road. That is what we are trying to find. So find the values of coefficient of friction static for which the car would slip on the curve. We are trying to make the car slip on the curve. That is our objective. So what is the expression which we obtained? So the expression which we obtained was square root mu gr, right? Something like this. Obviously, when the speed of the car exceeds this value, it is going to slip. If the value of speed goes below this value, it is going to not slip, right? But in this case, we are already having the speed of the car, and we want to find the coefficient of friction. What would be the value of mu for which the car does not slip? So we know the R, B and G. So how are we going to find mu? We can find from this expression, right? And from this mu we can refer the situation. So since we have already developed the block situation, we have already drawn the free body diagram of the car. That we mean to say that what is the forces acting on the car, what is the friction. We can directly use this expression and we can say that this is the limiting case, right? And in the limiting case, all the things are happening in the limits, that the maximum speed of the car is there. So for a given value of mu we are going to obtain v, or we can conversely say for a given value of v we are obtaining the minimum value of mu, or something like that. So let's just see the value of mu, which is coming like this. Mu, what would be the value of mu? It would be equal to v square, some v square divided by g into r. So this would be the value of mu. And let us try to use our intuition to answer this particular question, right? So from intuition we can say that if the value of mu goes greater than this particular value, v square by gr, then we would be able to say, right, the car would be not be slipping on the road. If the value of mu goes less than v square by gr, then we are talking about the case where the car would slip. This is what we require, right? So how is this happening? We have a car, normal force is acting on it, gravitational force mg. Even though we say that we won't be requiring to draw the free body diagram, we have just drawn it for our question's sake. So the force of friction F, which we have to require. So we are to find the force of friction so that the velocity which we have assigned to the case, that is 18 kilometers per hour, is sufficient to make the car slip. So the car must slip, that is the case which we have taken. So this means that the velocity, the friction force which we are going to have, we are going to have some friction force. This friction force has to be insufficient. We are not providing the friction force to the car so that it is going to not slip on the horizontal road as it is traveling. The friction force acting on the car has to be less than the force which we require to the car keeping in the circle. So that means, and let me reiterate this point, this inequality, that the friction which we are going to provide to the car, let's say F. Now this friction is going to reach its maximum to make the car stop from slipping, right? Point number 1. As we are going to make the car slip, the friction would reach its maximum possible value and would prevent the car from slipping, right? So this value F, it is going to reach mu mg. But let us keep it through F right up till now. The value of friction which we are going to provide, that particular value should not match the value which the car requires to keep it in circular motion. If it were to require, the car would keep going in a circle, but we have to make the car slip. So that means the maximum value which the friction can reach must not match the value which the car wants. The car wants mv square by r to keep it moving in a circle. So I hope that we are understanding what is the friction force required. The friction force required is mv square by r. This is what the car wants to make it go in the circle, right? But the question says that you have to find the value of mu for which the car slips. If the question was the car must not slip, then it say that the value of friction should be more than mv square by r. It has to keep the car going in a motion, but the car has to be slipped, right? So it say the value of friction should be less than what the car requires. It is mainly the idea, mainly the question of what is required by the particular situation and then not provide to it. So it is required that the car has the centripetal force provided to it mv square by r. The provider was friction and it is not providing that value of friction that we have said. That means we have met the condition that the car would slip. And there can be one more way of solving this question. We can say that, okay, what if the car were not to slip? If the car were not to slip, then we would say the maximum value of friction, that is mu mg, should be more than the force which is required by the car, mv square by r, right? So mu mg should be more than the value of centripetal forces acting on the car. So from this we can refer that mu should be more than or equal to v square by gr. That is the condition which we are evaluating here. So this means that this is the condition for no slip between the car and the road. So if this condition is not met, that means we are not able to provide this inequality values of coefficient of friction between the car to the road. If this is not true, then what is going to happen? Then the opposite of that is going to happen, that is slipping is going to happen. So we have solved this question with two particular kinds of approach. The first approach is that what is required, not going to provide that, and the second approach is that to provide that and then to directly go opposite to it. So the condition of slip is mu should be less than v square by gr, and we already solved it by intuition only. If the coefficient of friction is not high, then it is going to slip, right, like in the general cases. This is what intuition says. If the mu is high, then slipping won't be there. If mu is less, then the slipping is going to be there, right? So that should be what our approach should be to every question, that our intuition or what is going to happen should satisfy the equations which we are going to obtain. So the value of mu should be less than v square by gr. So what is the velocity of the car? The velocity of car is some 18 kilometers per hour. So 18 kilometers per hour comes out to be some 5 meters per second. So 5 meters per second square, v square divided by 9.8 divided radius of the circle is some 30. So this should be some mu. So let us say mu is some, let's say value of g is nearly some 10 meters per second square for the calculation's sake. So the value of mu comes out to be less than equal to 1 by 2. So from that we can demonstrate the idea that the coefficient of friction, when its value is less than 1 by 12, then the car is going to slip. So let us move on to our next question. So again we have a question, the road again the question is of similar type. So let us move on to our next topic. So the next topic, let us consider when a car is going on a road and it is going on a bank curve. Car going on a bank curve. So the first case which we are going to take is with no wear and tear of tires. So that's not what I have written, no wear and tear, but it's assumed no wear and tear of tires. So that is the case which we are going to consider now. So we have a bank curve, and on a bank curve the car is going. So by a bank curve we mean a curve like this, drawn like this. So again assume this is this to be a car. This is the car and it is going on a curve, and this curve has some banking. Banking means it has some inclination. So the radius of the circle in which the car is going some is r and is going with some speed v. So this is the situation in which car goes in a bank curve. It is usually used, banking is usually used to provide higher speed for the car so that it is able to go in a circle in a smooth manner. And with the with the further purpose of making the passengers feel comfortable when they are going in a circle and not get thrown out of their seats to the in radially outward direction. So next, you would say what is the velocity of the car that is moving in a circle. I already know the velocity of the car, that is some v, and we'd say what are the forces acting. So again, the combined normal reaction of all the four tires acting on the car, that is N, the gravitational force, that is mg, and the forces of friction. So since we do not require any wear and tear of the tires of the car, we would be taking the cases that the car is going in a circle with no requirement of friction from the road itself. If the friction would act on the car, it would act in either down the incline, so to speak, or along the incline, so to speak, and would try to create some unnecessary forces acting on the car. And it may be necessary in some cases when the car is going to have some different speeds, but we can totally avoid the speed to meet the condition, or those speeds to meet the condition of no wear and tear. So is it possible that the car goes in a circle like this on a bank with no requirement of friction from the road at all, even though in the previous case we had a friction acting on the car? But that is the advantage of taking a bank curve, that friction is not required at all. So what is the force which is going to take that car in a circle now? Friction is not there. How is it going to move in a circle at all? So the case is, the force acting in this direction is clearly the some component of normal. Since gravitational force is not there, by process of elimination we can easily say that the component of normal reaction is trying to take the car in the circular motion way. So we can take the component of normal force, or we can take the components of gravitational force. Both are equally acceptable approaches. So what is the direction of acceleration in which the car in the circle in which the car is moving? So the acceleration is directed in this manner. This is the acceleration of direction, some perpendicular to its velocity. The car is going like this, so its acceleration is acting towards this direction. So this is denoted by this particular arrow. So let us move ahead. What is the normal reaction? The angle of backing is some theta. So we know that this particular angle is going to be some theta. So since the car is not moving up and down the incline, it is not moving towards the center of the circle or moving away, the normal reactions component is going to balance the gravitational force, and the other component, that is n sine theta, this component is some n sine theta, it is going to provide the acceleration to the car towards the center of the circle. And similarly we can say the other component is n cos theta. The n cos theta is going to provide the gravitational force. It is going to balance mg. So from this we can easily say that tan theta is equal to a by g. Acceleration is v square by r, so it comes out to be some v is equal to square root rg tan theta. So possibly this particular part of the equation tan theta is equal to a by g is not visible in the video because of some reflection. So I will repeat it. N sin theta is equal to ma and cos theta is equal to mg. If we divide these two, we get tan theta is equal to a by g. So this is tan theta equal to a by g. On further solving this, we get v is equal to rg tan theta. So we have used the value of a is equal to v square by r. From this we get v is equal to rg tan theta. And let us do some questions on the basis of this idea. So the first question which we are going to do is the road. Again, the question which we are taking earlier, the road at a circular turn of radius 10 meter. So we have a circular turn of some radius 10 meter, and it is banked at an angle of 10 degree. So the angle of banking is given some 10 degree. The value of tan 10 degree is given as some 0.176. So the road is banked at some angle on which the car has to move. So the tan 10 degree is given. So you have to find the speed for the car for which minimum wear and tear of tires is going to be there. So again, the condition for minimum wear and tear is that we do not require friction to act in this case. All the work is being or all the forces are being provided by the normal forces. So the expression which we obtained was V is equal to Rj tan theta. Value of R is some 10 meters. Action to gravity G is, let us take it as 9.8. Tan theta, that's tan 10 degree, some 0.176. After evaluating this particular expression, we will get value of velocity as 13.1 meters per second. So again, some questions can come directly, like what is the value of velocity required for minimum wear and tear of tires, directly mathematical expression based. And some questions can come which require you to think the whole idea that why the coefficient of friction is required at all when the car is moving at a road, and what are the conditions of mu for which the car would slip, what are the conditions for which the car won't slip, and how do we obtain those conditions, how do we are able to verify our natural thinking with the mathematical expression which we are going to get. So thank you for watching and have a great day.